G'day and welcome to lecture 3 for week 7. We're continuing on looking at oscillators, only today we're going to be looking at damping and driving. So we're going to be expanding on our simple harmonic oscillator idea. Remember, simple harmonic oscillators just have one frequency, they're just set going, they're left alone, they don't gain or lose any energy. Today we're going to think about systems where they can lose energy or be given energy as they're going. So we'll jump on over to the slideshow and we'll see how we go. So damping and resonance is our slide. Right, so the learning outcomes for today. I'm not sure whether this will be 1 or 2 videos yet. I'll see how I go for time, but there's just the 2 topics essentially today. Damping, so we'll start off by defining damping, looking at the equation of motion for a damped harmonic oscillator, and then look into the terms underdamped, critically damped, and overdamped that relate to damped motion. And then we'll move on to driven harmonic motion, where we're going to look again at the equation of motion, and we're going to introduce something called the Q value that will tell us about an oscillating system. So a simple harmonic oscillator, such as a pendulum or a mass on a spring, will actually lose energy over time in the real world. So it won't actually be a simple harmonic oscillator. SHOs are an ideal approximation that we use to understand the system, but they're not really how things work in reality. So as I said, we've ignored this, but we are going to think now about what happens. So we call it damping. Damping can be different effects. The most common one is air resistance or fluid resistance. If it's not in air, it might be underwater or some other substance. So damping is that the term that just means that energy loss to friction or whatever else. As I said, it's usually due to it being in air or potentially some other fluid, because we don't actually have these systems set up in a vacuum, but it can be other things. Sometimes though, we want damping to occur. So if you've got a car with shock absorbers or suspension on it and you go over a bump, you don't want the car to sit there oscillating up and down for ages and ages and ages while you're driving along still. You want the shock absorbers to sort of smooth out the motion a bit, but for the car to quickly return to a nice stable point in terms of its height above the road. So we want damping in systems like that. That's what damping will achieve. To think about damping, to put it into equation terms, obviously is the goal of us as physicists. So we want to think about what numbers and what values we need. And there's really only one thing that we care about at this stage. We can make much more complicated models, but the first step from a perfect ideal SHO into starting to think about damping is to introduce what we call a linear drag model. So that means that the drag on an object is linearly related to its velocity. So we've got that as an equation here on the screen. The drag force is equal to negative BV, V being, of course, the velocity at any point in time, and B being the linear drag constant. So you'll notice that aside from it being linear, we've got this negative in there, and that just means that the drag force is going to be opposing the motion. And that makes sense because if something's traveling through fluid in one direction, the force on it will be back the other way. So the drag force will oppose the motion. And that's all we have to it. So we're just going to add that in. We're going to put this force in there and see what comes out. So when we think about what this will do to our system, it's going to lose energy every time it swings back and forth. And if it's losing energy, then remember that the peak amplitudes, the points where it got as far away from its equilibrium position as it could, that was when all the energy was turned into potential energy. And if we've lost some energy along the way, it can't end up with as much potential energy, which means it can't end up back as far away from the equilibrium position as it started. So essentially what we'll see is that with every oscillation, the harmonic oscillator loses some energy and therefore loses some amplitude. And so you can see here the blue dotted line is an undamped oscillator. That's what we've been looking at in the previous lecture. The green line shows us what happens when we have a damped oscillator. It's just one example. There's lots of different variables involved, but as an example, we've just got a slight damping that decreases a little bit each time, so that after however many oscillations there are on this graph, the amplitude is now well down compared to where it was when it started. So that's what we'd expect to see. That is what we see. But we still want to have a have an equation to define that. We still have oscillations, so we're still going to have the cosine term. You can see, sorry, just go back a slide, you can still see we've got this cosine term. It's just now being squished as time goes on. So as time goes on, that cosine term is being limited to a smaller and smaller range. Eventually, of course, it would get down and essentially look like a flat line. And that's not shown here. So we're still going to have a cosine term. That's not going to change, but we have to allow for this reduction in amplitude. So in simple harmonic oscillators, we just had A out the front of our cosine term. It was just the amplitude times the cosine term. But now that amplitude changes over time. So we can't just have A, we have to have A and another term that will decrease that A over time. So we bring in an exponential. Hopefully you've met exponentials in maths or in other courses. I'm not going to go into detail about exponential terms. You just need to accept that they do what we say they do, but do go and read up on them if you haven't met them before, or you're not sure, if you're not confident in them. Go and spend a bit of time just reading about exponential functions. So we bring in an exponential function, and we have negative bt over 2m. So remember, b was our drag coefficient, m obviously being the mass of our system in this case, of the oscillator, and a is that initial amplitude still. So we still start with A, but we now have this exponential term. You don't need to worry about where that exponential term comes from. Just trust us, that is the exponential term we need. And it gives us what we call a damping envelope. So I've left that, that decaying oscillator. It was a green line in the previous graph. It's now a grey dotted line, just so you can see where how it went. But what I've done here is I've just plotted that amplitude times the exponential term. So just this decaying amplitude, and that's the purple lines on this graph. We call that the envelope. We call it the envelope because the entire curve is contained within it. All right. So that envelope is defined by A, the initial amplitude, and that exponential term that just shows how quickly that will die off, how quickly those oscillations will get smaller. By varying that drag coefficient B, we get a quicker decrease in our envelope. So I've removed the actual oscillating path, and I've just included the envelope now. We've got the straight line, b equals 0. So when we've got no damping, then our cosine term never gets any smaller. We have simple harmonic oscillation, and our envelope is just a straight line that goes on forever and ever. But as soon as you have any drag coefficient, we start to get some damping. We get that envelope starting to close as time goes on. And so I've just got 3 randomly chosen values here, and they're all with mass 1 kilogram. And they just show you that if you start at amplitude A, then as you increase the drag coefficient, the amplitude decreases more quickly rather. That's bad English. Decreases more quickly. This time frame is only 1 second. So within 1 second, the B equals 0.03 kilograms per second. You can see it's just sort of decayed a bit, maybe half the way, but you've still got noticeable oscillations. The B equals 0.1 kilograms per second. After a minute, that will be very small, but you'd still notice it is oscillating. It is still going back and forth a little bit. But by the time we get up to a drag coefficient of 0.3 kilograms per second, that has completely died off. There'd be no noticeable oscillations. The oscillations would be less than the precision that we could measure them to after 60 seconds. They're almost gone after 30, 40 seconds. So you can see that the linear drag coefficient will have a dramatic impact on the outcome of your system. A lower B value, less drag, means it will last longer. Higher B value, more drag, it means it will die off very quickly. But what does this do to the oscillation time? When we had an undamped oscillator, we knew how to figure out how long it took to do one oscillation, right? We had ways to get the frequency or the period from our system properties. But what about when we've got drag? Because drag is slowing down the oscillator, that means that it's going to take longer to get to where it goes. Is it actually going to end up taking longer to do one cycle than it would have without the drag? The answer is yes, it does. Not by a lot, not by a great deal, but it does take a little bit longer. And obviously it also doesn't go quite as far as it did when it was damped, because it's now got a lower amplitude, when it was undamped. It's now got a lower amplitude for a damped oscillator. So this graph is slightly exaggerated, but it shows you the point. If you start both of these oscillators at amplitude A at time 0, let them go, they're both showing the reduction in amplitude we get from damping, but the green one shows that we also get an increase in period. Right? The time it takes to do an oscillation will be slightly longer as well. So we get a reduced amplitude compared to undamped, and we also get an increased period or a reduced angular frequency. So the angular frequency will be slightly less. What is the formula for it? At this point, it's useful to introduce new terms. We put omega with a little subscript 0 or naught for undamped angular frequency. And so we still calculate that the same way. For a mass spring system, it would be square root of K over M. But we now have a damped frequency, which we often write as omega dash or omega prime. And that is the square root of that undamped frequency squared minus B squared over 4M squared. Right? So the square root of that whole thing. Don't worry about where this has come from or how we got there. Just trust us, take our word for it that that is the formula. So while I don't want you to know how to derive that, I do want you to understand why we have this change, right? As the oscillator is being slowed down by the drag, it means it's going to take a bit longer to get to where it wants to get to. So we just get a slight delay in our angular frequency, slight decrease in our angular frequency. And obviously that's going to depend on this drag coefficient and the mass. So hopefully you can understand that that all is relevant without needing to worry too much about the derivation. So that puts us in a place now where we can write out our equation of motion for a damped harmonic oscillator. We still have our amplitude out the front because that gives us our initial height that the system was set to, but it now decays according to this exponential term, that envelope that we talked about. So we get A times the exponential. And we still have our cosine term, but now we've got to use our damped angular frequency, omega prime times t plus phi naught. We can still have our initial conditions in there with our phase constant. You'll notice that we've also put a new term in there, gamma, in that exponential, exponent of negative gamma t rather than bt over 2m. We've just brought in gamma as b over 2m, which just simplifies that equation a little bit for us. And you'll also notice that it allows us to write omega primed as the square root of omega naught squared minus gamma squared, which again is just simplifying. It doesn't change the formulas, just a little bit easier for us to write and manipulate equations using gamma instead of b over 2m. So that is our equation of motion for a damped harmonic oscillator. Hopefully you can see where the terms in that come from, why they're different from a simple harmonic oscillator, and obviously be able to use that equation to do some simple calculations. As I said, we don't expect you to be able to derive these things. We just expect you to understand and interpret them and apply them. But if you are interested, it comes from the force considerations and Newton's second law. So the mass that's on the end of our spring times the acceleration, ma, has to be equal to the net force. In a simple harmonic oscillator, the net force was just the restoring force. It was just negative kx, and that was a very simple equation, ma equals negative kx. But now we've got this extra term, negative bv, because we've got a damping force as well as the restoring force being equal to the net force. So the next line here is just rearranging that and remembering that acceleration is the second derivative of x with respect to time and the velocity is the first derivative of x with respect to time. It means that we can write that out in this format, which is a second order differential equation, which again we don't expect you to be able to solve, but you could check that the equation we've given you does work for this if you were really keen, but the point is this is where it comes from. If you continue on with your studies, you'll learn more about this. We teach it in second year physics. We talk all about the derivation of this. But for now, just being aware that it comes from these force considerations is generally enough for you to be happy with what we've told you. So far, we've talked about damping that just decreases the amplitude a little bit each time. But what happens if we increase the damping more? What happens if we increase it so much that it actually doesn't oscillate at all, right? Imagine putting a mass spring system inside a jar of honey, and you pull down on the spring a little bit and let it go. It's not going to start oscillating because it's in honey, right? Honey is very thick, it's tough to move through the oscillator. The mass will just slowly creep back up to its equilibrium position and stay there, right? There'll be no oscillating at all. In this sort of situation, the damping coefficient is so big, the motion doesn't ever oscillate. And we call that over-damping. Over-damped as in it's damped beyond the oscillating possibility for the system. So that's all over-damping means. We've just got a drag coefficient that's so high we don't get any oscillating. But there's a special value that borders between over-damping and under-damping. So under-damping is just all the damping we've seen so far, the regular damping. It's under-damped as in it hasn't yet reached its critical damping. So critical damping is the value of damping that means the mass will return to its equilibrium position as quickly as possible without oscillating. Right, so if you've got something in honey that will creep back really slowly, now imagine it in something that's less thick than honey, but still thicker than air, maybe something like water, and you pull it down and let it go, it'll return to its equilibrium position quicker, but it might not still oscillate. There will be some damping coefficient that will let you return that object to its equilibrium position as quickly as possible without oscillating at all, and that is called critical damping. And that's actually a really important idea, a really important concept, because there are a lot of systems where we want that to happen. Like I said earlier at the start of the lecture, if you've got a car with shock absorbers, you want it to be displaced, then quickly return to its equilibrium position without ever oscillating. And that's critical damping. So if we can set shock absorbers to be critically damped, that's ideal. If it's slightly less, then you'll get a slight oscillation. If it's slightly more, then it'll take too long to return and you might hit another bump before it's returned, and the system's not prepared for that next bump, and you end up getting shocks that aren't absorbed properly. So critical damping is ideal for a system like that, but also things like buildings responding after earthquakes and things like that. So there's a lot of systems where critical damping is a very useful situation to have occur. So as I've said, we've got damping types. The damped angular frequency is the square root of the undamped frequency squared minus gamma squared. We already met that. If omega naught squared minus gamma squared is greater than 0, we have a positive term in the square root, and that's great. We can do maths with that. That's called damped, or just underdamped, as I mentioned before. The value inside that square root goes to 0 when omega naught squared is equal to gamma squared, and we call that critically damped. And that's the one that we're looking for when we want it to return as quickly as possible to its equilibrium position. And if the omega naught squared value is less than gamma squared, then the value inside that square root becomes negative, and we're dealing with imaginary numbers, and obviously that doesn't make a lot of sense. That is where we have overdamped, and it's imaginary because we don't have an angular frequency for an overdamped system. There is no oscillation, so we can't have a frequency. So those are the different types of damping. As I said, damped can also be called underdamped. I'll add that in for the slides on the website, but I didn't have that here on the video, but it can be underdamped as well. And this is just a table that shows those damping conditions. We've got the ones in the center are the ones I just talked about, but remembering the definition for omega naught for a mass spring system, and remembering the definition for gamma, we can actually rearrange those to put them in terms of B, the damping coefficient for any specific system, and that can sometimes be a more useful format to look at the damping conditions. So we've got an example now of a mass spring system. We've got a 4 kilogram mass hanging on a spring with a constant of K equals 392 newtons per meter. Determine the value of the drag coefficient that will result in critical damping. And then another part to the question is, if the drag coefficient is instead 6.5 kilograms per second, what is the period of the damped system? And compare it to what the period would be if the system were undamped. All right, so we've got some working to do on this. We'll jump over to the document camera and we'll just have a think about this, this system. So as usual, first thing to do is to write out what we know. We have been told that the mass is 4 kilograms. The spring constant is 392 newtons per meter. And we're being asked what is the drag coefficient that will result in critical damping. So what is B for, if we go back to our critical damping slide, you can, if you've got it in front of you, you can look at it. I just went back on my slides. We get B squared equals 4mk. That was the condition for critical damping. So that's pretty simple. We just have B equals the square root of 4mk, and we've been given 4m and k. Oh, we've been given 4, that's a number. We've been given m and k. So we can just put those values in. And if I just get my calculator, put in 4m and k, we get the square root of 4 times 392. And I get that to be 79.2 kilograms per second are the units there. So B is kilograms per second, 79.2. That is the first part of the question. Nice and easy, use one formula, put the values in. Second part of the formula is the one where we need to start thinking about some more things potentially. So the second part of the question is, now set B equal to 6.50 kilograms per second. And what is the period of the damped system? So I'll call that T prime, and compare it to T naught, the period of an undamped system, if it weren't damped. So we just look at our formulas for the adjusted angular frequency. So we're looking for a period, but obviously our formulas all tell us about the angular frequency. So omega naught, omega prime is omega naught squared minus gamma squared, and omega naught is equal to the square root of k over m. So we're looking for t, but we've got to calculate the angular frequency first, and then once we've got the angular frequency, we just remember that that is equal to 2 pi over omega. So omega prime for that one and omega naught for that one. So that's what we're looking for. Now that we know we're looking for that, if we figure out this omega naught, that'll give us T naught, but also let us put it in for omega prime. So we'll do that one first. Omega naught is just square root k over m, which is square root 392 over 4.0. So I get out 392 divided by 4, 9.8995. I'm not going to throw away any decimal places yet, just because I don't know how big the difference between these will be, and that's what we're interested in, the difference between T naught and T prime. So if we've got 9.8995, now I can do 2 pi divided by that to get our period. 2 pi divided by, answer is 0.63, again, I'll keep a few extra decimal places just for now. 6347, we'll just go there, 6347 seconds for a period. So that's our undamped period, but the question obviously is asking us to figure out what the damped period is so that we can compare them. We've now got omega naught squared. Gamma squared is going to be, if you remember gamma, so gamma, you can look back through your slides, and it was B over 2m, but we've got squared, so B squared over 4m squared. And so we can put in our values for that, and we get out B squared is 6.5 squared divided by 4 times the mass squared, which was 4 squared again, 4 squared. So I get 0.66002-ish. So now what we do is we put this value, right, this one here, goes in for omega naught squared, this one here goes in for gamma squared, and we can calculate our omega prime. So that comes out to be, according to my calculations, 3.0, that doesn't seem right. I didn't square them, that's why. That's better. That comes out to be 9.8775. So we had 8995, now 8775. So it has decreased slightly, which is what we expected for a damped system. And now we do 2 pi divided by that to get our damped period. 2 pi divided by answer, 0.6361. So our period for the damped oscillator is at when B is 6.5 is 0.6361 seconds, and when it's undamped it's 0.6347 seconds. So we can see that it does change slightly, but not a huge amount, right? So there is some change to our to the period of our oscillator as we expected. So I'm actually going to end this video here now. I'm just looking at the time frames. I'll make it 2 videos like I have with the others, 3 with the questions at the end. So we'll leave that there, and the next video we'll pick up by looking at forced oscillations, which is where we're giving energy into the system. So to this lecture, this video was just about damping, where we can lose energy from the system and therefore lose amplitude as time goes on. Next, we're going to think about what happens when we start pushing the system, when we drive it and give it some extra energy.